component 2 in class question book, question 11. And we're in inheritance, and we have another blood system called MN. And we have codominant alleles, and they code for proteins in the membrane. That's not too important. The Hardy-Weinberg principle states that allele frequencies in a population remain constant. State these three conditions. So these are what you should definitely get from here. And there's probably about 4, 5, 6 conditions. So things like random mating, and kind of a infinitely large population, no immigration, emigration, and another possibility here is like no selective advantage, no selective advantage, and we could have no mutations. So 3 pretty straightforward marks there. Then we have our 2 classic Hardy-Weinberg equations, and our bit of information here that we really need is we're associating 45% with our allele N, and there we go. So P is M, Q is our N. Okay, the percentage frequency of allele M. So we've got 45% for N. So this is our equation that we want. So P plus Q equals 1. So I just need a different colour. So if I use pink for M, so that is our P there. So P plus Q is 1, and we know what Q is. Q is 45% or 0.45. So that's the information that we're using, and as a percentage, so 100% minus our 45% equals, you just do this in your head, that's 55%. So that's the answer there, 55%, because the 2 frequencies add up to 1, or in this case add up to 100%. The number of individuals in a population of 10,000 with blood group M. Well, we need to use our other equation now, so we're using our P squared plus 2PQ plus Q squared equals 1. And our number of individuals is, well, these are our ones that would be MM. These are our homozygous. Here's our heterozygous, and here are our homozygous again with N's. So we're going to use Q squared, M is the other one. So we're wanting these guys here. So you're wanting those guys there. And so we can, so P squared is 0.55 times by 0.55, so 0.55 squared. When you do that on your calculator, 0.55 times by 0.55, that gives you 0.3025. So that is the proportion of our population, if population was 1, proportion that are homozygous for M, so the MM. But our population is 10,000, so we need to go, so in 10,000 we've got 0.3025 times by 10,000, which is 3025. And now for the next, we're doing exactly the same thing. 2pq plus q squared equals 1. So that's our equation that we're using. It's asking for the population with blood group N. So that is the people who are homozygous for N. So these guys here, these have got blood group N. And so we're doing the same thing again. We're doing q squared is our frequency up here, so 0.45. So 0.45 times by 0.45, and then we've got our 10,000 again. So 0.45 times by 0.45 times by 10,000, and that's 2025. And then we're almost doing the same thing for individuals in population group MN. So equation again, plus 2pq plus q squared equals 1. These are those guys there, MN. So now it's 2 times by p, and so p was 0.55 times by q, which was 0.45, and then that times that by 10,000 again for our 10,000 population. So 2 times by 0.55 times by 0.45 times by 10,000 is 4950. Do these numbers sound sensible? Well, in a population of 10,000 they should add up now to 10,000. So when you add up those, you can see, you can add them up on a calculator, they add up to 10,000. So it's a good way of checking 3025 plus 2025 plus 4950. That adds up to 10,000. So we're pretty sure that we're not too far away there. So over the page we've got some sort of AO2, AO3 type of information to look at. So we've got a population that moved away and then largely, inbred population over time. Looking at this data, what do we notice from this data? So our emigrated group, which, how do they compare? They've got more homozygous N's and less homozygous M's. So they're different to the other two populations. Certainly in the homozygous traits of N and M. So why could this have happened? So the clue really here is, married almost exclusively within their communities. So that should give you, that's what we're really talking about. What happens when you only inbreed within a small population. So even if you don't really like this graph, that's the bit of information that we're after. So things like, you know, the founder effect or genetic drift. So an isolated population will only have its original alleles from the founders to go on, and they will multiply in the population as new individuals are born. Genetic drift, well, that's a small population, you know, will have mutations that are exclusive to that population, or, you know, numbers of alleles exclusive to that population, and that will move away from a general type of population. And the founder effect is probably easier to think about. And in this example, so using this information now, so they seem to have a high frequency of N's and low of M. So we can say that. So a high frequency of N, low frequency of M in this population. And then we just, you know, reminding ourselves that there's no mating with the general population. So we're coming back with this bit of information here, and that's why they were able to stay so different as a population. So no mating with the general population. No, if we use the right word, gene flow, you know, from that population into the general population. So a little bit more tricky for those last 3 marks, but certainly you should have got 3 marks, and certainly the first of the maths. And really, if you've done a lot of practice, those are pretty straightforward as well. So 3, 4, 5, 6, 7. So 7 out of 10. Even without this one, that's enough to get you an A.